In this video, let's do some problems on group actions and stabilizers and orbits. Okay, so I want to do some problems in this video. Let's start with the following. So let's start with some calculation of stabilizers and orbits. Okay, so let's consider the action of, let's take G, consider the action of a group G on itself by left multiplication. We know from the from viewing the action as an equivalence relation, we know that a group G, the set S, when a group G acts on a set S is partitioned into orbits, right? S is a disjoint union of orbits. Find orbit decomposition of S. G, and similarly find the stabilizer of an element S in G. Okay, this is the problem. Because G is partitioned as a disjoint union of orbits, so I want you to find all orbits of G and see what are the orbits whose disjoint union is G. Similarly, given an element small s, find its stabilizer. So recall that here the action is given by left multiplication. G comma S maps to GS, right? So this is the action. Let's compute the order. So let us first take an element, let's first compute the orbit of an element. In order to find the orbit decomposition, let's start with finding the orbit of single element. So let's take S in S. What is the orbit of S? So orbit of S is GS, as by definition it is the set of elements GS as G varies in G. Now this is something that I have implicitly done several times, but the point is this is equal to G. So of course orbit is contained in G always, G being thought of as a set here, but in fact orbit is equal to G, because if T is in G, then G, let's say S T inverse, sorry, so if T is in G, we want to find a group element such that G times S is equal to that. So what should that be? We want, so how do we check this? We want GS to be T, right? If T is in G, I want to show that T is in OS, but OS consists of GS. So GS must be equal to T for some G. So I want to solve for G. So G would be T S inverse. So we take T S inverse times S is T. So that means T is in OS. So orbit is G, and this is, remember, for all S in G. So what is orbit decomposition? So there is exactly one orbit. For this action. There is only one orbit for this action. In other words, all orbits are identical to G. So this such an action is called transitive action. So I will define this maybe formally again in some other video, but this is an example of transitive, means only one orbit. Okay, So this is the orbit decomposition. So we have done the first part of the problem, right? Write the orbit decomposition. So G is equal to OS, that is orbit decomposition for any S. Right? That's the orbit decomposition. It is in general a disjoint union of orbits, but there is only one orbit here. Now on the other hand, let us take an element S, in this case G, find the stabilizer. That was also the problem, right? What is GS? This is all elements of the group now that fix S, right? All elements of the group that fix S. What are these? If GS equals S, a quick calculation tells you, and this also we have done earlier, is just so orbit, the stabilizer of any element is just E. Okay, and this illustrates the counting formula that we have done. So think for a moment that G is finite. Remember that for any action we have, recall the counting formula. Counting formula says that order of the group is equal to number of elements of the orbit times number of elements of the stabilizer for a fixed element. Here again S is an arbitrary set and G acts on it. So remember the dynamics here. This left hand side is fixed. If for some element there is a large orbit, the stabilizer must be small. If the orbit is small, the stabilizer must be big, because the product of these two is order of G. So large orbit, loosely speaking, this implies small stabilizer. Small orbit implies large stabilizer. Okay, correct? Small orbit means OS is small number of elements, so GS must make up for it because the product is order of G. So very loosely speaking, this is a heuristic that you should remember. In this case, for the group action given by left multiplication, orbit is very big as it can be. So stabilizer is very small, as small as it can be. One element, all elements. So that is what happens in this problem. Let's do problem 2. Do the same for the action of G on itself by conjugation when G is abelian. Okay, so let's assume in this problem that G is abelian. Let's find out orbit decomposition and stabilizers for this action. What are these? So now remember the action is given by GS G inverse. That is the action, conjugation action. So what is the orbit of an element? So orbit of an element, let us fix S in S or S in G. What is orbit? This is GS G inverse, as G is inside G. But I am assuming G is abelian. So that means GS G inverse is just S. So no matter what small g is, this is just S. Right? And what is a stabilizer? So here the reverse happens as opposed to the previous example problem. Here orbit is very small. Orbit is as small as it can be. It only consists of that element. On the other hand, what is the stabilizer? This is G in G such that G S G inverse is S. Right? Things that fix S. under the action GS G inverse is the action of small g on small s, so that must be equal to s. But this is G in G such that s equals s, but there is no condition. In other words, for all G in G this condition holds, so this is G. So here orbits are small, stabilizer is big, right? Stabilizer is as big as it can be, it's all of G. So orbit decomposition would be G would be union of singleton elements. Earlier there is only one orbit in the previous example, so there is just one orbit. Here there are as many orbits as there are elements of the group. Okay, so this is the orbit decomposition. Let's do problem 3. Show that, so now again consider the action of G on itself by conjugation. So I am not going to assume now that G is abelian, G is an arbitrary group. Show that two things. So let S be an element of G. Show that stabilizer of S is the centralizer of S. I will recall in this problem what is the centralizer. So stabilizer of S is the centralizer of S, and show that S belongs to the center of G. I will also recall for you what is the center of the group, if and only if stabilizer is all of G. Okay, so this is the problem. So let us solve this. So I am asking you to show that the centralizer of S. So I am going to recall, let G be an arbitrary group, and let's take G in G. Centralizer of G, which I have denoted by C of G, I think, is all elements which commute with G. So A in G such that AG equals GA. Remember, this is same as saying that A in G such that A inverse is G. What is the center of G, of the group G, which I denoted by ZG? This is elements of the group that commute with everything else. Okay, the center will always be contained in centralizer of any element. So this is all elements such that A inverse is G for all A in G, for all G in G, right? So this is the centralizer and center that we have defined earlier. Now for the action of conjugation, action of G on itself by conjugation, show that the stabilizer is the centralizer. Now what is a stabilizer? This is almost clear from the definition now, right? Because GS is by definition G in G such that GS G inverse is S, the stabilizer of S, right? Stabilizer of S is by definition this, but this is of course the centralizer as I have written here. If you just stare at the two things, it is all elements such that when you take the conjugate of G or this particular element, you get that element back. So it is, of course I am confusing with the letters here. Here I am using A and G, here I am using S and G. But hopefully it's clear that stabilizer of an element of S, of an element S, is all G such that conjugate of S by G is equal to S, which is the centralizer of S. So this is the first part of the problem. Now suppose, so second part of the problem is an element is in the center if and only if its stabilizer is G. Suppose S is in the center. If S is in the center, this means Sx or rather I should write SG equals GS for all G in G, right? This is the meaning of being in the center, which is same as G S G inverse is S for all. These are all if and only if, right? They go back and forth. If S is in the center, this happens. If this happens, then S is in the center. This is clearly equivalent to this. But this means G belongs to stabilizer of S for all G in G. Right? If GSG inverse is equal to S, that means G is in the stabilizer. So if this GSG inverse is S for all G, then G is in the stabilizer for all G. Similarly, if G is in the stabilizer, GSG inverse is S. But if G is in stabilizer for all G, that is equal to this. So S is in the stabilizer if and only if GS is equal to G. This is the second part of the problem. That also I have shown. Okay, so now let's look at a different action, so different example. So let's look at problem 4. Here I am going to consider the action of the group of invertible n by n matrices on the set of column vectors. Here the action is given by A dot V is AV, where AV is matrix multiplication. Okay, so here again find orbit decomposition of Rn, and 2 find the stabilizer of the elementary vector E1, so that is 1 0 0 0. So two problems. Okay, let's solve this. Find the orbit decomposition. So I have alluded to this when I did this example and did orbit, so let me quickly do this. First of all, if you take the 0 vector, the orbit of 0 vector is just the 0 vector, right? Because any matrix times 0 vector is this, is the 0 vector. So this is an orbit by itself. So this is one orbit. On the other hand, there is only one more orbit. There is only one other orbit because given any non-zero vector, any non-zero vectors V1 and V2, right? There exists an invertible matrix A such that A V1 is V2. So this is something that I said is a fact, and I don't want to prove this now, but you can check this easily at least when n equal to 2. So check this, I will leave this as an exercise for you. For n equal to 2, it's very easy to check because it's all 2 by 2 matrices and vectors of length 2. You can easily cook up a matrix which achieves this, given V1 and V2. That means all non-zero vectors form an orbit. Right? Is that clear? Because I am saying that any two vectors, given any two non-zero vectors, there is a matrix which sends one to the other. In other words, any two non-zero vectors are equivalent. So all non-zero vectors together form an orbit. So what is the orbit decomposition of Rn? You have the 0 vector as one orbit. So there are, and all non-zero vectors as one orbit. So there are exactly 2 orbits. For this action. Note that all counting formula and so on don't make any sense here because the group is infinite and the set is infinite. So we can't get anything from counting formula. However, we can say that the set is a disjoint union of orbits, that always holds, irrespective of finiteness of the group or the set. And in this case, the two orbits are 0 vector by itself and non-zero vectors by themselves. So this is the orbit decomposition. Modulo this fact, which I will leave for you to verify. In general also it's not difficult, and n equal to 2 is especially easy. Now let's do the second part. What is the stabilizer of E1? So this is, so GE1 is my notation for this. So these are all matrices in GLN such that AE1 is E1. Let's work it out a little bit. Let's write a matrix like this. It's an n by n matrix, right? So the first entries row are A11, A12, A22, A2n. Finally, the last row is AN1, AN2, ANN. And if you multiply this with E, this is A, E is 1, 0, 0. What do you get? If you are familiar with matrix multiplication, this is simply A11 times 1 plus A12 times 0 and rest do not contribute. So that's just A11. The second row times the vector here will give you A21 up to AN1. So this is the first row, first column rather. Okay, this is a property of matrix multiplication. When you multiply the matrix with the E1 elementary vector, you get the first column. But what is the, if A is in the stabilizer, then AE1 is E1. That means the first column of the matrix A must be 1, 0, 0, E1 itself. And there is no other condition, right? So stabilizer of E1 or GE1 is matrices such that the first column of A is E1. Okay, more clearly it would be all matrices of this form. The first column will be A and the rest is anything. This part is arbitrary. Of course, it must be something in GLNR, right? So stabilizer of E1 is, because remember there is no condition on A12, A1n, A22, A2n, AN2, ANN. They do not contribute to the product at all. So they can be anything. Only the condition is first column must be in 1, 0, must be E1. This is arbitrary. Star means it can be anything. But in a way that this whole matrix forms an invertible matrix. So this is the stabilizer of E1. So this is the problem, right? We have shown that orbit decomposition of this is the 0 vector union non-zero vectors, and we have computed the stabilizer of E1.